Hello, and welcome to the April webinar from the IEA Clean Coal Centre. My name is Debo Adams, and I'm Communications Manager here. Our monthly webinars are based on our technical reports, which are available from our website, www.iea-coal.org. Residents of member countries and employees of sponsoring organisations can download our reports at no charge after one-off registration. Please visit our website for details. My colleague Xing Zhang is presenting today's webinar. Her topic is the microalgal removal of CO2 from flue gas from power plants. The report has been out for review and will be published soon. Then it will be available from the website. If you have any questions during the talk, please ask them using the Ask a Question box at the top of your screen. Add your email address as well, so that Xing can send you a fuller answer if she runs out of time. Okay, Xing, over to you.
Thank you, Debo. Good afternoon from London. Welcome to my webinar. My today's webinar is based on my latest study on microalgae removal of CO2 from flue gas. The final report will be published shortly. In my presentation, I will first discuss why it is possible to use algae to capture CO2 from flue gas, then briefly introduce algae capturing method and harvesting processes. Available applications from algae will be covered, but the focus will be on the development in using algae to capture carbon dioxide from coal-fired power plants. I will list the demonstration projects and discuss two of them in detail. This is a flow chart of microalgae capturing CO2 from coal combustion flue gas. After going through the pollution control systems, the flue gas is pumped into algae pond for algae to grow. The concept of using the CO2 in the flue gas from a coal-fired power plant to produce microalgae and then converting the algae biomass to fuel was first studied over 50 years ago at the University of California, Berkeley in the United States. The possibilities and advantages of capturing CO2 from the flue gas by microalgae are as the following. First, algae is not very fussy with the purity of CO2. Flue gas can be fed directly to the algae culture. Secondly, NOx, SOx, and some heavy metals in flue gas can be used as nutrients for algae to grow. Thirdly, algae can yield high-value commercial products, which will offset capital and operating costs. Some argue that algae carbon fixation is a renewable cycle. It has very small negative impact on the environment comparing to the conventional CCS. The theory behind algae capturing CO2 is photosynthesis. It is estimated that more than 50,000 algae species exist, and numerous species have been identified that are able to fix inorganic carbon in the environment. However, unlike air, which has a low CO2 content, flue gas typically contains 4 to 14% or more CO2. Flue gas also has a high flow rate, high temperature, and possible toxic compounds. This means that the algae species need to be able to tolerate the harsh flue gas conditions in order to mitigate the CO2. Species such as Chlorella, Nanochloropsis are known to grow well under flue gas conditions. Microalgae CO2 carbon fixation is a complex physical-chemical process. Apart from algae species, the process is also influenced by culture parameters, including physical, chemical, and hydrodynamic parameters. Details of these parameters are discussed in my report. Today, I'm only going to briefly go through the factors related to flue gas. Physical-chemical affecting factors are listed here. First, CO2 concentration. As I have just mentioned, flue gas typically contains 4 to 14% of CO2, but most of the algae grow only at low CO2 concentration levels. Above 5% CO2, their growth is inhibited. Some algae can grow under higher flue gas CO2 concentrations, but the carbon fixation and the biomass production rate are reduced. The NOx, SOx, and some heavy metals in the flue gas also influence algae's growth, but the effect is still not fully understood. Some researchers have found that NOx, SOx, and trace elements can act as nutrients for the algae, while others have found them toxic. Room temperature around 18 to 20 degrees is often recommended, so flue gas needs to be cooled down before pumping into the algae culture medium. Usually, low pH value reduces algae's growth rate. The pH in the culture medium depends on the carbon dioxide and the sulfur dioxide concentration in the flue gas. Appropriate turbulent flow and mixing are necessary to homogenize the cells' light, heat, nutrients, and metabolite distribution, to enhance mass transfer and to prevent microalgae aggregation and sedimentation. Mixing also takes advantage of flashing light effect, which increases algae growth. Excessive turbulent flow and mixing may damage the microalgal cells, besides requiring a large energy input. There are two types of algae culturing systems. One is open pond, the other is the closed system, namely photobioreactors. The advantages and the disadvantages of the two systems are compared in this table. The biggest advantage of open ponds is their simplicity, which leads to low production and operating costs. However, this system is easy to get contaminated and difficult to control the temperature and the light. CO2 can diffuse to air, water may evaporate, and worst of all, it requires large areas of land to accommodate the pond. The carbon fixation rate for open pond is quite low. The closed system can avoid all these drawbacks, but it is expensive to build and to operate. Commonly used methods for algae harvesting are listed here. My report includes more details for each method. Once algae are harvested, the algae slurry must be dried for stability and for other processes. algae may need further extraction and purification depending on the applications. Coal-firing dried algae biomass with coal to produce electricity is the easiest and the most obvious algae application. But since microalgae contains lipids, carbohydrates, proteins, and some fat, algae can be converted into commercial applications such as human food, animal feed, cosmetic products, medical drugs, and so on. For the power generation industry, these applications can be an extra bonus. Algae have been investigated to make biofuels. American company Algino have produced bioethanol and biodiesel from algae in commercial scale based on its patent direct-to-ethanol process. There are also some reports on using algae for wastewater treatment. Microalgae can process hazardous or toxic compounds in wastewater since they produce the oxygen required by bacteria to biodegrade the pollutants. But my interest is in algae's carbon capture and utilization ability. Although it has the same drawbacks as conventional carbon capture and storage method, namely a large energy requirement and high equipment costs, CO2 mitigation by algae can be classified as carbon capture and utilization. This is due to the production of value-added biomass. Here, carbon dioxide becomes a feedstock instead of a waste product. Scientists at Algino published a paper in March this year. They compared CO2 emissions from 3 scenarios at a powerized coal-fired power plant. They are algae bio-fixation, conventional CCS, and no CCS at all. Please have a look at the top picture. For algae biomass fixation scenario, 1 megajoule of electricity is generated. Capture the released CO2, use it to grow algae, and use the algae to make ethanol, which can generate 4.6 megajoule of fuel energy. When this 4.6 megajoule ethanol is combusted, it releases 330 grams of CO2. The total CO2 released in this case is 429 grams. For the conventional CCS case, CO2 emission from generating 1 megajoule electricity and combusting 4.6 megajoule petrol is 451 grams. And for no CO2 capture case, the CO2 emission is 707 grams. So algae bio-fixation does have an advantage. It is also worth to point out that although the carbon used to grow algae is still released when combusted, the overall amount of carbon has been used twice. Once for electricity generation in a power plant, and the second time is to grow algae for fuels. The same calculation was carried out for another 3 different power plants, namely natural gas, IEACCC, supercritical coal. As you can see from the bottom figure, all 4 power plants yield the same conclusion, that is, an integrated algae ethanol biorefinery can make significant CO2 reduction. The ordering for carbon footprint is powerized coal is greater than supercritical, greater than IGCC, and greater than natural gas. This is because pyrolyzed coal-fired power plant releases the most CO2. There are many current research and demonstration projects on utilizing flue gas to grow algae. Here, I only listed some pilot projects that are related to capturing carbon dioxide from coal-fired power plant and have the culturing facilities close to the plant. I'll discuss two of these in detail. Symbiotic was the first company in the world to utilize flue gas from coal-burning power stations for algae cultivation. Its pilot facility was established in 2006 and is located at the Israel Electric Corporation's Rutenburg coal-fired power station, close to the city of Ascalon. The algae are cultivated in open ponds using the flue gas and the effluent from cooling seawater condenser, piped directly from the power station. The pond is about 100 to 150 meters away from the stack. The total pond surface area is about 1,000 square meters. The flue gas approaching the pond is at ambient temperature with approximately 12% of CO2. Seawater is supplied from the turbine condenser cool water system of the power station's discharge terminal. According to a document on the company's website, using flue gas instead of pure CO2 has pushed algae productivity up by 50%. This is probably due to the existence of SOx, NOx, and heavy metals such as zinc in the flue gas, which act as nutrients for algae to grow. The second example is a closed system from America. The Center for Applied Energy Research at the University of Kentucky has started working on demonstrating algae capturing CO2 since 2008 and has the biggest demonstration site in the United States at the Duke Energy's East Bend coal-fired power plant. The plant has a single 650 megawatt unit with wet scrubber and SCR installed. The flue gas used in the pilot plant was obtained after the scrubber and SCR treatment. The center designed these closed-loop vertical tube photobioreactors. The photobioreactor was installed and started operating in December 2012. The results they have got so far are very promising. In summer months, the algae productivity can achieve 30 grams per square meter or more a day. In December, the productivity is around 10 grams per square meter per day. The center also developed a low-cost, low-energy protocol to process algae. Extraction of lipids from harvested biomass was demonstrated, followed by their conversion to diesel-range hydrocarbons. The harvested algae biomass contained an average of 42.5% of carbon and 66.5% of volatile matter, with no detectable concentration of trace elements. The absence of heavy metals is an encouraging factor for utilizing the algae for high-value applications. Using their approach, the cost of capturing and recycling CO2 will be reduced to 550 tons of CO2, assuming a payback period is 30 years. The most expensive part of the process is the algae capturing stage because of the high capital cost of photobioreactor system and the associated installation. Conclusions. Theoretically, using fast-growing algae to fix carbon dioxide from a coal-fired power plant is a promising alternative to conventional CCS approaches. Compared to CCS approach, microalgae carbon mitigation is more environmental friendly and sustainable, and it does not reduce the thermal efficiency of the power plant. However, microalgae CO2 fixation is a complex process, especially in flue gas environment. The process is influenced by a number of factors that are related and interact with each other. It is crucial to consider the effects of all the factors in order to improve algae growth and its tolerance to the environment. The choice of algae species is important as they directly influence the photosynthesis efficiency and hence the performance of carbon fixation and biomass production. The two algae growing systems each have their own pros and cons. Technologies used to harvest, process, and produce valuable products from algae are not developed specifically for algae production. They are adapted from those already in use in the food, pharmaceutical, and wastewater treatment sectors. Therefore, they are inefficient and require a large amount of energy input. These are the areas that need to be investigated in order to improve the economics of algae carbon fixation. Keeping algae cultivation systems close to power plant is a good idea to avoid the cost of building long pipelines for CO2 transportation. So far, only the Israeli company Symbiotic has commercially produced significant quantities of algae from open pond system using the flue gas from a coal-fired power plant. In terms of research and development, America is leading the way. My final thought on this topic. The CO2 fixation rate of algae tends to be too low to compete with the conventional CCS method, especially for the open pond systems. Using flue gas to culture algae is more applicable to the production of high-value products, such as biofuels, than carbon fixation. Power companies will only be willing to invest large amounts of capital, land, and water if the algae product can be sold at a good price. Algae companies are almost ready to bring their carbon capture and utilization efforts to the marketplace. They need a large, constant amount of CO2 for the technology to work. However, Those algae strains which can thrive under flue gas conditions do not often have a high commercial value. If algae companies have to pay the power companies to reuse the flue gas, they may not have the motivation to produce low-value algae biomass. Therefore, it is very important for algae companies and the power companies to form a win-win partnership to share the costs and the profits. Another potential advantage of the algae CCS approach is the combination of CO2 fixation and the biomass production and wastewater treatment. It is clear that microalgae capturing CO2 from the flue gas is technically feasible and has an economic potential. But before cheap, efficient photobioreactors become available, the industry needs political support to endorse the technologies and applications. Thank you for listening.
Xing, thank you very much for a really interesting presentation. While we have a look and see what questions have come in, can I just remind listeners that Xing's PowerPoint will be available to download from the webinar page of our website later on today. Okay, we already have a couple of questions coming in. The first one, Xing, have you calculated the surface area that an algal production system would need to have enough capacity to sequester CO2 from a flue stack? Well, I guess it depends on how much CO2 is emitted from the flue stack, but over to you, Xing.
I believe you are referring to the open pond system. It does request a vast amount of area of surface. And as I mentioned, the open pond system, the efficiency of capturing CO2 is quite low. So I must say this is a drawback of the open pond system, and indeed for the algae capture CO2 system to sequester CO2 from flue gas. I haven't calculated the surface area that algal production system myself, but I believe the scientists at University of Kentucky, they did some calculation, and some people in Australia did the calculation as well. They have published a report, in Australia. It can be downloaded. If you need further information regarding this report, please email me.
Thank you, Xing. Now, the next question is one that had crossed my mind as well. What happens at night? So the second part of it is, what is the capture rate over a 24-hour period? Because I guess when the algae aren't photosynthesizing.
As you know, algae need light to grow, and this is one of the reasons the efficiency for algae capturing system is low. I suppose for the closed system, one can use artificial light, but I think at night probably they will just have a rest. But bear in mind, the algae growth need light and a dark cycle. So the ratio of this cycle also affect the efficiency of the capturing.
Thank you, Xing. Okay, the next question. What is the growth medium used in all the case studies you've mentioned? Because the nutrient cost can be up to 30% of the total cost of operation.
The nutrient cost for growing algae is significant. I believe the algae companies do bear this in mind. But for my report, my interest is use algae to capture CO2 from the flue gas in the coal-fired power plant. So one of the advantage of this approach is some belief the NOx, SOx, and some heavy metals in the flue gas can be considered as the nutrient.
Okay, there's a lot of questions coming in today, Xing. If Xing does run out of time, please remember to put your email address with the question or email Xing after the session and she'll get back to you with as much information as she has. Xing, here's another question. How about employing a consortium of robust microalgae instead of just using one single species?
I think to increase the efficiency, especially for our purpose to capture CO2 from a coal-fired power plant, we are interested to select fast-growing, high-efficiency fixation species to use in our bio-fixation approach. Whether you can mix different species together, I haven't really considered in this factor in my report.
Thank you, Xing. Now, do you think we could use industrial effluents to grow algae and do carbon capture as well?
Yes, this is one of the advantages, I believe, for algae bio-fixation approach. As I mentioned earlier in my presentation, I think the algae might be able to use the element in the wastewater as a nutrient, and also use the carbon in the flue gas to grow.
Thank you. Now, the next one is more of a comment, and it says in India, NALCO, which is NALCO, has recently installed a system for flue gas mitigation. So thank you. That's interesting for Xing. I'm not sure if she's included it in her work, but it's something that she'll look up if she hasn't. Now, Xing, there's one more question come through. Zing, you mentioned that the carbon fixation rate for algae is quite low compared to conventional CCS. How low is it?
Hi. For the Indian comment, I'm sorry, I haven't got the information on this. Could you please email it to me? Thank you. A report from Australia mentioned algae growth could only consume around 20 to 25% of the total CO2 output in flue gas. For open pond, some reported the carbon fixation rate can be as high as 40%, and some reported it can be as low as 10% of CO2 emitted by the power plant was captured. For the closed system, the capture rate is much higher because the affecting factors can be controlled. In theory, for closed system, it can reach 100%. In reality, it is much lower. In laboratory, above 80% in a sunny day was reported, and 50% was reported by many researchers. According to the Australian report, as I just mentioned, it could be around 25%. I have to stress this approach is not efficient enough comparing to the conventional CCS approach.
Thank you. Oh, and thank you very much to the listener who's already sent in the link to NALCO. If you are interested in Zing's report, do contact her, and I'm sure she'll be able to send you a copy. There's another comment from India, which says that FICO Spectrum has installed algae-based treatment plants in Indian industries. So thank you. I'm sure Zing will follow up on these websites. Now we're coming to the end of Zing's presentation now. So just to remind you that her PowerPoint will be available to download from the webinar page of our website later on today. And the next webinar from the IEA Clean Coal Centre will be presented by our colleague Toby Lockwood on Wednesday 13th of May, again at midday UK time. His topic is a very different one to Zing's, and his research has been on advanced sensors and smart control systems for coal-fired power plants. So thank you all very much for listening. If you've got further comments, do email Zing. Thank you. Goodbye.